How's everybody doing?
Good.
Good?
Good.
Great.
Wonderful. That's what I like to hear.
How are you?
I think I'm okay. Very, very stressed today
That's
trying to
good.
get all of this stuff figured out. You're class number 3 this morning, so
Oh boy.
yeah, so a little bit stressful, but that's all right. We'll figure it out. I'm trying this through my hotspot, so if it dies, somebody email me and let me know. Otherwise, I'll just keep talking. Any questions about anything before we get going? Was the video okay that I sent out to? Videos, I guess.
Yes.
Yes? All right. So, today we're going to start some new stuff, but I want to review a little bit with the F distributions. Is the only thing that you've seen with that, I believe, is just the video that I sent out. I don't think we actually did anything with a hypothesis test with determining whether or not variances were equal, and that we know that that was an important consideration back when we were doing hypothesis testing for two means, especially when we had small samples. If the variances were equal, we pooled the variance. If we thought the variances were equal, we pooled the variances together to get us a standard deviation estimate. But if the variances we thought might be unequal, then we used Welch's T to do the hypothesis test, and it decreased the degrees of freedom. So we had to have a little bit higher of a value of a test statistic to be able to reject the null hypothesis. So I want to go through another example with using the F distribution to test variances being equal, and then talk about, I am sharing good, and then talk about the new stuff with one factor analysis of variance, and do a little bit of stuff on Excel after I go through a little bit of a long-winded explanation of to get to that point. So, all right, we already know that our F distribution, remember, you have to have a chi-squared divided out by its degrees of freedom, and divided by another chi-squared with its degrees of freedom. So U is chi-squared of R, V is chi-squared of S. And one of the things in the video, and then also in your book in section 7.4, they go through and say that if you're doing the hypothesis testing that the variances are equal, or that the ratio of the variances is 1, and then your null hypothesis is that it's not 1, that would be two-tailed, or you could do less than 1 or greater than 1. You could do your corresponding one-tailed tests. If we're assuming that the variances are equal, then you can create your F distribution by doing your sample variance transformation to get the chi-squared, and then divide out by its degrees of freedom, and do the same thing with the sample variance for y. Okay, so remember again that this part that I'm circling is chi-squared of n minus 1. And then this part is chi-squared of m minus 1. So this is all just stuff that we've talked about in the past. So if we're assuming that... Sorry, go ahead.
Keep breaking out.
Oh, I keep breaking out? Yeah, part of that's probably the fact that I'm on my hotspot. Can you see the screen okay?
Yeah,
Yeah.
there it goes.
Oh, okay. Okay, cool. Yeah, holler if there's something that I need to repeat, definitely. All right. So, again, this stuff hopefully is review stuff. That we talked about this being chi-squared and this being chi-squared. Now, again, remember, we're assuming, when we're doing our hypothesis testing, we're assuming the null hypothesis is true. So we're assuming that the variances are equal to each other. If they're equal to each other, then those variances cancel out. And then notice that your degrees of freedom pieces cancel out as well. So this just ends up being sx squared over sy squared. So this is how we get our test statistic in this particular case. And then we use our F distribution to get our critical values. So let's switch over to Excel. And I know that you're still on that particular share. Let's see here, new share. Share Excel. Oh, then it pops Excel open for me. That was nice of it. All right. So we've got, this is, I found some data. There's a website called Kaggle, Kaggle, which has all sorts of different data sets that you can play with. So this particular data set was a whole bunch of information about hotel reservations around the world from 2015 to 2017. That's where I got these numbers from. And what these numbers represent are lead times from when the reservation was made to when the person actually showed up at the hotel. So I just took a random sample of the data that was in that particular file, and I'm gonna post a video later of how you can quickly randomize data and grab a sample out using Excel. I'll show you how that works. So anyway,
Dr. Joe,
yeah,
are those in minutes or hours
or these are days.
Oh,
Yeah, it's days. It's days from when it was booked to when they showed up for their reservation. All right, so let's say that we wanted to test whether or not the U.S. and Australia had different variances of the lead times into when they were actually going, when they made the reservation, and then when they were going to actually show up at the hotel. So to do that, let me move Mexico out of the way for the time being, and I'll use Mexico here in a minute. All right, so let's do our sample variances. If I can spell the word variance. All right, so over here we'll use that var.s command again, and I will just highlight the data to get the sample variance for USA is 62 and change. And then here for Australia, we get 13,431 and change. All right, so there does look like, at least from just looking at the numbers, looks like there's a discrepancy between the variances, but we still need to test to see whether or not this actually is enough evidence to tell us whether or not there's a discrepancy. So we need to figure out the critical. Let's do a two-tailed test for this one. The one-tailed test, you would find these values in a similar fashion. Now let's see if we can figure out the critical value. So there's going to be a lower critical value and an upper critical value. Remember that the F distribution is not symmetric across the y-axis. So if we want to do a two, just like the chi-squared is not symmetric across the y-axis. So if you want to do a two-tailed test, you actually have to find two critical values one for the lower tail and one for the upper tail to be able to conduct your hypothesis test. All right, to get these values, we're going to use the F distribution functions that are built into Excel. All right, we have a probability, we have a significance level that we want to achieve. We need the critical value. So that's why we're going to use the inverse command here, the f.inverse. So the f.inverse, that will give you a left tail. The f.inverse.rt will give you the right tail. So for this one, for argument's sake, let's say we're going to do alpha is 0.05. Again, you get to decide that, or it'll be given to you in the problem. Since I'm doing a two-tailed test here, I'll have to split the alpha in half. So we'll use 0.025 for the probability for the lower and for the upper. So degrees of freedom 1, that's going to be the degrees of freedom in your numerator. Since we're doing since we're doing a two-tailed test, it really doesn't matter which one we put on top and which one we put on bottom. So I'm just going to do the USA on top and Australia on bottom. I could do it the other way around. It doesn't matter. The only thing that matters is where you put in for your degrees of freedom, for whether this is going to be your numerator degrees of freedom, this is going to be your denominator's degrees of freedom. So if I'm going to do the degrees of freedom for USA as degree of freedom 1, I need to make sure when I do my test statistic that I take the variance for USA and divide it by the variance for Australia. All right, so there are 25 numbers here in the sample size for the USA. Remember, for degrees of freedom, we're going to subtract 1 off, so we'll have 24 for degrees of freedom 1. There are 18 for Australia. Again, we subtract 1 off, so 17. So that gives us our lower critical value. Do the same process for the right tail. We had 24 for the numerator and 17 for the denominator, and get that. Everybody okay with where I got those numbers from? Any issues?
Dr. Joe, you've been cutting out really bad for like the last minute.
Okay, I'm sorry. Are you able to follow along okay? Did I cut out again? Can everybody still see my screen?
Yeah, I can see your screen.
Okay.
I haven't been able to hear you.
Okay. Is everybody able to follow along without, or do I need to repeat some of the stuff I said?
I didn't. The screen cut out and your words were cutting out, so I have no idea what just happened. It like sped through a bunch of things.
Oh, it sped through a bunch of things.
Like click on the critical values Excel thing.
Okay, so here, yeah, I figured part of this was going to be issues with hotspot. So I apologize. All right, so here, what we're doing with the critical values is looking to find the cutoff would be for the lower 2.5%. So that's why I've got the 0.025 here. What just happened? That really cut the screen. That really cut out.
Oh.
Hello.
I think we're still in it. He's the one that's out.
That was
He
fun.
says he's the host now.
Who's that? Oh, I want to see those.
You can't be the host.
I know, I'm not fooling them.
Hello. Oops. Hello.
This is.
Oh, he's back.
I am back. How are you?
We're doing alright.
We're getting there.
We're getting there. Can you see my screen again?
Yes.
Yes.
Okay.
I can see it now.
Wonderful. This is what happens when you try to run off a hotspot. All right. Well, at least my other two classes seem to go okay this morning. At least from the feedback I got so far. All right. Anyway, back to the critical values. Are we okay with how I got these critical values, or do we need to go back through it again?
What was that? I didn't hear what you said.
You're cut up again.
Well, of course I did.
The screen is frozen.
You know, the screen is frozen?
Oh, it's working now.
I moved my iPad to a different spot. Maybe I could get a little better reception. Well, I've had problems with the hotspot with it just randomly cutting my computer completely off and then just never finding it again. So I've actually got the computer tethered to the iPad right now with a USB cable. Can you hear me?
Yeah.
Okay, cool.
Better now.
All right.
Yeah.
I don't know how it's gonna last.
Yeah, well, we'll hold our breath. Well, at least I'm recording all of this so you can go back and watch the disaster that's happening. All right. So critical values again. Here we go. So using the f.inv command, we're doing a two-tailed test, so that's why I'm using the 0.05 cut in half. The 24 is the USA sample size -1. I'm going to put it in the numerator. And the 17 is the Australia sample size. I'm going to put the one less than that. I'm going to use it for the denominator. We okay with that?
Yeah.
Yep. Okay. And the only difference between that and this one is the fact that I'm looking for the right value. I'm looking for the upper tail versus the lower tail. So that's why I've got the .rt, but the arguments are the same for the function. So since this is a two-tailed test, we're going to compute our test statistic. We'll reject if we're below this lower one or above the upper one. And then for our test statistic here, we'll again, we use degrees of freedom for the USA values as our numerator. So I'll take the USA variance and divide it by the Australia variance. And we got 0.51. Oh my gosh.
It was working this morning during linear algebra.
I'm back again.
Better than
Stuff is probably just done. Yeah, it was working better.
yeah, it's probably done for the day.
It's yes. Everybody hear me now? Hello.
Yeah.
Yeah. I don't know why it's being such a pain. Well, it could also be that we're getting to a more popular time for Zoom.
We're cutting out.
Nope, you're turning into a computer again.
I'm turning into a computer?
Yeah, you sound
It sounds
like
like
a
a
computer, Dr. Joe.
I am a robot.
So can you explain again how you got the right tail? Did you use the degrees of freedom for Australia on top or USA? That part was all cut out.
I used the right tail, so I still had USA on top and Australia on bottom.
Okay.
What was the TS?
This is just the ratio of USA to Australia.
Okay, that's right.
Dr. Joe, how come it's different from what we did a little while ago where we did like the 1/f of that stuff?
When you do the 1/f of that stuff is when you're using the table, because the table only goes in one direction. So to use the table to go the other direction, you have to do the reciprocal. When you use Excel, you don't have to worry about it.
Okay.
That's why we're doing it this way. I'm trying really hard not to worry about it. We good with that?
Yes.
Yes. Okay. I thought maybe you couldn't hear me again. Okay. Now, at least I know when it's kicking me off of Zoom and it's trying to reboot it, because I thought before I would just have to be talking to myself and none of you would know that I was gone. Or you would know that I was gone, but I wouldn't know that you were gone. All right. if you wanted to do a p-value with this, all right, so to do the p-value, we will use the f.dist command. We want to, this test statistic is below 1. So I would want to know what the probability is that you are below that value, and then we would need to double it, because remember we're doing a two-tailed test here. So I'll do the f.dist command, grab the test statistic, put in your degrees of freedom for numerator and denominator, and then say cumulative. Now again, the reason why I'm going below is because it's below 1. If this value were above 1, I would do the f.dist.right tail to get the probability above it. Okay. And then so this would be, I would need to take this. Would be the p-value for a one-tailed test. Since we're doing a two-tailed test, I would need to take that value and double it to get the p-value for this test. So our p-value in this case is 0.129-ish. And again, the only reason why I had to double it is because remember for p-values, I have to worry about being not only below but above. Are we okay with F distribution stuff?
Because the p-value is greater than our alpha, that means we do not reject.
We do not reject, right? Yep, that's correct.
So for the F distributions, for normal, the mean is usually it's a 0, 1.
Yes.
If it's standardized for an F distribution, is that mean supposed to be 1?
No, the mean depends on lots of different things. The mean depends on what the degrees of freedom are for not top and bottom. So there's, let's see, I don't even remember what page it's on. Is it in the front of the book? I'm not sure the F distribution is in the front. No. I'd have to actually look up where the mean, what the mean is for the F distribution based on. But it's like the chi-squared. Remember the chi-squared? The mean depends on the degrees of freedom. It's the same kind of concept for F. It depends on what the degrees of freedom are for what the mean is.
Okay.
So we're not standardizing it to one specific distribution. We're standardizing it to a distribution based on the degrees of freedom that we have. So the different properties of the distribution would change depending on what distribution, or excuse me, what the degrees of freedom are. Does that make sense?
Yeah.
Okay, cool. All right. So are we okay with F then? And try to do something else here?
Yeah.
Yes.
I don't think so.
Okay. All right. So I want to talk about the next section, which is analysis of variance. So we're going to have one factor and wait for that to go by. One factor and two factor analysis of variance. So I don't know how much you've kept up with the news in the last couple of days, but there's been this talk of being able to use a couple of different drugs, one an anti-malarial medication and one an antibiotic to help fight the coronavirus, people who are already infected with it. Now, someone who was supposedly a doctor at got his MD from Columbia University, had said that there was some clinical trial that came out that was talking about being able to eliminate the virus within 6 days based on some patients. And they had supposedly 3 different groups going on. One was a control group, so they got none of the medicine. One only got one of the medicines, and one got both of the medicines. And we're trying to determine whether or not these medicines were actually having an effect. So the idea behind this is, besides the fact that the clinical trial wasn't a trial at all because it was non-random samples, it was small samples, there was all sorts of issues with the particular trial. You may have heard talk about it in the news or not. But the point of the whole thing is that you've got 3 different groups that you're trying to analyze all at the same time and see what happens. All we have done so far is analyze at most 2 different groups at one time. So the idea of this analysis of variance is to try to see if there is a difference among multiple groups versus just 2 groups at the same time. So the setup is the following, and I hope this is somewhat legible because I decided to handwrite it and copy and paste things into PowerPoint rather than type the math because I was trying to be lazy, trying to get lots of things done at the same time. So the idea... Say that again?
What does the text say?
It says several independent populations.
Okay.
Yeah. So we've got several populations. So more than... the idea here is more than 2. I mean, you can do it with 2, but it's pointless since we already know how to handle 2. So you have several populations. We're assuming that they're independent. We're assuming that they are all normally distributed, but have the same, perhaps have different means, but all have the same variance. Okay? So we're going to call those populations X1 out to XM. And we're going to take random samples from each population. So the way the notation goes for the subscripts is that the first subscript is referring to the population that you're in, and the second subscript is the whatever number of how many things you're in their sample. So for that second subscript for that first line is an N1. So what they're saying is that the sample from population 1 has size N1. And then the same thing down the line, the sample from population 2 has size N2, and so on. Okay. The reason why I'm doing this is because I'm trying to get the notation down before we start going through formulations of things. That's the only reason why we're doing that. All right, so then for the notation for each of the sample means over here on the right, the sample means have this notation, and I don't know why anyone would ever have used this notation. I hate it, but this is what they use. We have 1 and then a dot. So this is saying the sample mean from population 1, but apparently they really felt like they needed to put a dot here because for reasons, I guess. I don't know why. But that's what all these dots mean. Don't worry about the dot so much. It's not that big of a deal. It's just that this is sample mean 1. So it's the sample mean from population 1. This is the sample mean from population 2, and so on down the line. And then to get really stupid, we have a different notation for the overall sample mean. So treating all of these as one big sample, if you do that mean, you get the overall sample mean, which they put a double dot at the bottom. Again, I don't know why, but that's what they do. All right. So we need to make a hypothesis test. So the idea for the hypothesis test here is that all of the means are the same as your null hypothesis. Your alternative hypothesis is all other possibilities, which just means that one of the means is different from all of the others. So that's what we mean by this particular hypothesis test. All right. So we need to create a test statistic to be able to test this. So we're going to do this by using the variance. All right. So let's just use a single letter N to denote the overall sample size. So the sum of all of the smaller sample sizes. If I'm talking about the whole big thing as one big sample, we can calculate the sample variance like we always do, right? I just need to do the difference of data point minus sample mean and square it, add it all up, and divide by n minus 1. So this double sum, just make sure that we add them all up. So this is just calculating sample variance for the overall thing, you treating it as one big sample. We refer to this double sum without the n minus 1 in the denominator. We refer to this as the total sum of squares. That's what the TO stands for, total sum of squares. That's the SS. So SSTO is total sums of squares That's without the n-1 piece. All right. It's a sample variance. So if I multiply, this is a sample variance. So if I multiply by n-1 and divide by the variance, I get a chi-squared distribution. I know what the distribution of this piece is. In particular, the distribution of this piece is if I divide out by its variance. This is why we're going through this. We're just going through the different pieces and reminding ourselves of what these things are. All right. By the way, I'm never going to make you reproduce this. We're just trying to figure out where this test statistic that we're going to come up with comes from. That's all I'm trying to do with this discussion. I'm not going to make you reproduce all of this stuff, so don't worry about that. All right. If we wanted to do the sample variance for each population, we would do it the same way. I just wouldn't have a double sum. I would have a single sum. So this is just going from 1 to n sub I, whatever that I happens to be. I'm doing, again, the difference between sample point, data point, and mean, sample mean. This is fixed for a particular I, so I'm just running across a row, if you will, squaring the differences and dividing by n-1. Okay, so this is a sample variance treat individually for each population. That's all I'm saying here. Again, if I take that and multiply it by n-1, divide it by the variance, I get chi-squared of n sub I minus 1. All right? So, now, if I add all of these up...
Dr. Joe, pretty much everything you just said, nobody heard.
Oh, wonderful. Can you hear me now? No? All right. Can anybody hear me now? This is working so well. Can you hear me? Hello? Nobody can hear me.
Dr. Joe, it's just frozen on your face right now. It's so funny.
Hello?
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 Oh, no. Hello.
Hello?
No.
I can kind of hear you.
I kind of think, any better now? No.
Oh,
Not-
God. You're still a computer.
Wonderful.
That was a little bit better.
Was it better now?
Yeah.
Okay.
Yeah.
All right.
Yeah.
Where did I cut out?
When you were about to take sample variance of each population.
Okay. So for the sample variance for each population, we have the difference. We're just going across each row and calculating the variances. That's what this means. So notice that this sum here is only depending on the j. The I is fixed for each particular row. So we're just summing across a row for each individual one. So if we multiply that by n sub I minus 1 and divide by the variance, we get a chi-squared random variable. So all this next line here is, if we add up chi-squareds, they're all independent. So if we add up chi-squareds, we still get chi-squared. So when we take this entire double sum here, which is basically each of the data points minus the individual sample means, we get a chi-squared of n minus m degrees of freedom. We refer to this double sum on top as the error sum of squares. So that's what the E is standing for, is error. Everybody still hear me?
Is that the same statistic that was on that table if we use the data analysis?
Yes, we're going to do that. We're going to do that again. Yep, that's right.
So we're not going to actually have to calculate this.
Oh, no. God, no. We're going to use Excel.
Okay, perfect.
Yeah. I'm just going through where the pieces come from. That's all. All right. So let's break apart this total sum of squares. So the total sum of squares from the previous slide is this piece. I'm going to add and subtract in the individual sample means and square and FOIL, if you will. All right, so I see in the first piece, this is your SSE. This is your error sum of squares. I'm going to focus on the last term right now. So notice that in that last term, this piece has no J's in it. So I can pull it out in front of the sum that does have a J. I can't pull it all the way out because it has an I, but I can pull it out in front of the one with a J. I can rewrite the x sub ij as n sub I times x bar sub I dot. This is how you would compute this sample mean. You would take the sum of the x sub i's and divide. This has no j's in it, so when I add it up, n sub I times, I get n sub I times x sub I dot. Notice those two pieces are equal, so you get 0. This shouldn't be a huge surprise because you've seen this idea before when we've multiplied out things like this with squares and add up individual deviations. They tend to add up to 0, and that's exactly what happens in this case as well. All right, so what we have is that our total sum of squares is made up of two particular double sums. The first one's your error sum of squares. Your second one is what's referred to as SST. It's what's referred to as the between treatment sum of squares. And this second piece here simplifies to this single sum here. So this second piece here is the same as this second piece here. Just when you add it up, n sub I times. Notice this has no j's in it, right? There's no j's here. So this piece just becomes n sub I times what's on the inside. All right. So this part is your SSE. This part is your SST. Now, we already know that SSTO, the total sum of squares, when we divide it out by our variance, that's chi-squared of n minus 1. And we already know that our SSE, when we divide by our variance, is chi-squared of n minus m. So we don't have enough machinery to prove this right now, but you can kind of guess that if this piece is chi-squared and this piece is chi-squared, this piece also has to be chi-squared, and the degrees of freedom are going to have to match. So to get from n minus m to n minus 1, I have to have m minus 1 degrees of freedom. And again, m here is the number of different populations that we have. Okay. All right, so how do we create a test statistic? All right, so anyway, I'm not going to go, just because of time and internet connectivity issues, I'm not going to go through all of the explanation for this piece. But the idea here is that I already know that we're assuming that everything here has the exact same variance. So all this stuff here that I just clicked through quickly, I'm not going to go through all the explanation. I'm just trying to get to the whole point of this. Each of the individual pieces that you have for the populations all have the exact same variance. So that the expected value for your SSE, when you take it times, let's get to this point here. Let me get to where I'm going. Trying to get here. All right. So looking at this last line here, if we simplify all of this, I'm looking at the expected value of SST. Notice when you get to that, and like I said, this is just a bunch of algebra to get to this point. And like I said, in the interest of time and internet connectivity issues, I want to get to the actual point here. Notice that when I do the expected value of SST, I get m minus 1 times sigma squared, which is our common variance, plus this summand piece. But if we're assuming that all of the means are equal, this piece is going to be 0 no matter what. If they're not equal, then this is going to be something that's positive because we're squaring all of them. But in particular, when I get to the expected value, I get m minus 1 times sigma squared. We already know that our error sum of squares, our SSE, already has a chi-squared distribution of n minus m, n minus m degrees of freedom. The expected, the mean of a chi-squared distribution is the degrees of freedom, the n minus m. So when we do the SSE and divided by its degrees of freedom, its expected value will also be sigma squared. So the whole point of this is that if I take my SST and divide by n minus 1, I get an unbiased estimator for sigma squared. If I take my SSE and divide by n minus m, I also get an unbiased estimator of sigma squared. We're already saying that both of these are chi-squared distributions as well. This is what I mentioned on the last slide. The expected value of this goes up if the means are unequal. So this is how we're going to create our hypothesis test, our test statistic, if you will. So if I take the ratio of these two things, if the means are equal, then I should be getting this unbiased estimate of sigma squared. Since my sigma squared is equal all the way through everything, this ratio should be close to 1 if the null hypothesis is true. If the null hypothesis is not true, if at least one of the means is different from the rest of them, then this expected value is going to be bigger than the variance. So then this ratio is going to get bigger. Now notice what we have here. We've got these chi-squared distributions that are divided out by their degrees of freedom. So I've got this particular ratio now is an F distribution if I stick the sigma squared on top and bottom. I really do get a chi-squared divided out by its degrees of freedom, a chi-squared divided out by its degrees of freedom. That's an F distribution. So just like what we were talking about with doing the F test, we could create a critical region based on this F distribution. Okay, so that was the reason why I wanted to go all through all of this, is that when I get to this point, when you do this sum of the between treatment sum of squares and the error sum of squares, you get two chi-squared distributions. So you can create an F test out of it to be able to tell whether or not one of the means is different, or suspect that one of the means is different. Now, Grace asked the question earlier, and I already answered it, but I'm not going to make you do this by hand because that's a lot of different subtracting and squaring and all of those things. So let's talk about how we would use Excel. So let's see if I can get to new share. And let's get over to Excel. Let's say I delete all of this stuff out and delete this piece out. I want to compare the means now of these three particular sets of lead times. So I'm going to see does the mean lead time for USA, the mean lead time for Australia, the mean lead time for Mexico, are they the same or are they different from one another? Or I'm sorry, is at least one of them different from the others? All right, so to do this, I'm going to use the data analysis tool. Well, I was going to use the data. Oh, that's why. Where's my data analysis tool? Where did it go? Well, maybe I'll use the data analysis tool if I can find it.
Joe, I have a question real quick.
Sure.
So because your SSTO is your SSE plus your SST, does that mean it's also an unbiased estimator as well?
Yes, if you do the SSTO divided by the its degrees of freedom, the n-1, it will also be an unbiased estimator of the sigma squared. Yes, that is correct. Why are you not showing me what I want the data? Oops. Yeah, I know. I stopped the screen sharing on purpose because I can't get the data analysis to pop up. It was there yesterday when I was going through this stuff. Okay, so if I open... Okay, it's there now. Try this again. Sorry about that. Do you see my screen again? All right. Data analysis. Sorry about that. We want to go up to ANOVA single factor. So this one that's up at the top here. That's the reason why it's called analysis of variance, by the way, is because we're using the variance to create the test statistic. Even though we're doing a test of means, that's why we call it analysis of variance. All right. Input range. We want to take all of these values. So all I did was I was in the input range box and I just highlighted all of the data values. You can group your data by columns or rows. You can set the alpha value to whatever you want it to be. You could also have it put it in a new worksheet if you want. I'm just going to put it in this same thing. I'll click in the box and maybe put it over in E2 to start with. Doesn't matter where you put it, just so that we can read it. All right, so here is what comes out. So let's talk about the different pieces. In particular, this bottom piece right here. So we've got source of variation. We've got between groups. That's your between treatment sum of squares. This is SST. Notice there are 3 groups. So the degrees of freedom for that is 2. Remember, it's m-1. It's number of different populations minus 1. Within groups, that is your SSE. So that's the sum of all of your individual differences there, your error sum of squares. That is n minus m. That was your degrees of freedom for that. So if you take the 25, the 18, and the 30, you get 73, and there are 3 treatments, so that's why there are 70 degrees of freedom there. Overall degrees of freedom is 72, that's n minus 1. All right, it calculates the F statistic for you. It does SST over degrees of freedom. That's what this is your MS, if you want, MST or MSE. This is mean square error for both of those 2 pieces. So this is your sum of squared treatments divided by its degrees of freedom. This is sum of square error divided by its degrees of freedom. The quotient of these 2 is your F statistic. That was what we just created in the PowerPoint slide. Okay? So that's where this F statistic comes from. It's the quotient of these 2 pieces. This is your critical value based on 0.05 alpha. Degrees, numerator degrees of freedom would be 2. Denominator degrees of freedom would be 70. That's how they're getting this 3.128 here. Okay? And again, the reason where this is coming from is because each of these pieces have those chi-squared distributions. I just wanted to tell you where the different pieces come from. You're basically just reading this off a table, which anybody can read it off of a table, right? I can tell if this number is bigger than that number or not. But I want you to know where it came from, which is, I mean, kind of the point of going through this class is understanding where these things come from. You can always use it somewhere else. Yeah, sorry.
So the SS between groups, that's the SSE.
The SS between groups is SST. This one is T. This one is E. Oops. Or it's a euro symbol, one of the 2. I hate automatic substitution. All right. So in this case, we do not reject, right? Because the p-value is greater than 0.05 or your F statistic is less than the critical F value. So we do not reject. So there's not sufficient evidence to conclude that the means are different.
So, Dr. Joe, is it one tail?
This is always going to be a one-tailed test, yes. And the reason for that is because the SST, its expected value is either exactly the variance if the means are equal, or it's always greater than the variance if the means are unequal, which means that this test statistic that you're doing here will always be bigger than 1, no matter what.
Is the ANOVA double factor than a two-tail, or is that just...
That's something different that we're going to talk about in the next section.
So the value that we're looking for, like in this chart, is the F value that it gives?
You're comparing the F value that it gives to the critical F value that it gives, or reading it off the P value. So yeah, it's this piece of the table that's the important part, the part that I just highlighted.
So to get our conclusion, we're comparing the F to the F critical value?
Correct. That is correct. So it's almost exactly like what we just did for the at the beginning of this, well, disaster, I'll call it. I don't know, maybe that's too harsh. But at the beginning of this lecture, it's the same idea, right? We calculated an F statistic by doing the ratio of two variance-like statistics, and then compared it to a critical value based on our F distribution.
Okay, so since that's less than, we're not rejecting.
Correct. Since it's less than, we're not rejecting, right? Or equivalently, since the p-value is bigger than our alpha value, we're not rejecting. All right, questions on that? I apologize for the... Oh, sorry, go ahead.
No, I was just saying not anymore right now.
Okay. I apologize for the internet connectivity issues. Hopefully Wednesday it won't be as bad. If it's going to continue to be bad, we'll have to figure out something else to do. But we'll give it a go again on Wednesday. Again, I've recorded the lecture, so if there's something that you missed with me saying, you can go back and watch it. I will post it just like I've posted videos for class in the past. I will get another video of doing this analysis of variance stuff up using Excel. So if you were having trouble following along, I'll get another video up there as well. I'll get that later today or tomorrow morning at the latest. I'll make sure that you have that so you can see that. So anything else?
Dr. Joe,
yeah.
When it does summary and when it gives the sample variances for each, does it divide by n-1 or by n?
It should be dividing by n-1. Those should be sample variances.
Okay.
Should be. We can check real quick. Yep, it's doing n-1. It's a sample variance. I would have been surprised if it had done it the other way. Any other questions at all? Yep. All right. Well, I'm gonna.
Wait.
Sorry.
When you're doing your virtual office hours,
I'm going to do one tomorrow at 11. But if you've got, I'm thinking I'm going to send out a doodle poll to everybody in all 3 of my classes to see what times might work best for me to do that. But I'm definitely going to be on there tomorrow at 11. But you can always feel free to email me, and we can always schedule a time to do a chat through Zoom or something along those lines. And if you've got questions.
so when you have it, will it be over Zoom or just through email?
Oh no, it'll be over Zoom. I'll send out an invitation to the meeting.
I see. Thank you so much.
Oh, you're welcome. Anything else?